This lesson is about the 5 types of chemical reactions. It corresponds to Roman numeral 3 in the Unit 9 Honors Notes packet. The first type that we're going to discuss is combination reaction. It's also known as synthesis, and it's exactly what it sounds like. By definition, a combination or synthesis reaction is when 2 or more substances combine to form a single compound. Remember that substances can either be elements or compounds, and when they combine, it has to be a compound. For example, the 2 elements sodium and chlorine combine. Now let's think about what they could become. What are the 4 types of substances to consider when writing out an equation? There are single atoms. There are diatomic elements. That's what sodium and chlorine were. Sodium was single, chlorine is diatomic. However, it has to make a compound when they come together. So is this ionic or covalent? Remember that ionic compounds have metals with nonmetal. Covalent compounds have only nonmetals. So since sodium is a metal, chlorine is a nonmetal, it has to be an ionic compound, sodium chloride. You should be able to predict what that ionic compound's formula is going to be. Sodium's +1, chlorine is -1, so the compound will be sodium chloride, NaCl. If this were a covalent compound, you could not necessarily predict what it would be because covalent compounds are going to be determined by how many of each type of atom there are. Now, once we have this compound, it's important to balance it as well. The equation says 1 Na on this side, 1 Na on this side, 2 chlorines on this side, only 1 on that side. So what we need to do is get our chlorines balanced out. We can put a 2 right here. That's going to make 2 sodiums. So I also need to put a 2 right there. Now I have a balanced chemical equation. This is combination because 2 substances made 1 compound. Here's another example where the product is now a covalent compound. So I had to tell you what it was because sulfur and oxygen have more than one possible combination. In covalent, we use the prefixes instead of the charges. Sulfur dioxide means that there's 2 oxygens. So we have S plus O2 yields SO2. Next we have decomposition. In a decomposition reaction, a single compound is broken down into 2 or more substances. So this is the opposite of combination. Now we start with the compound and it's broken down into the parts. For example, what is hydrogen and oxygen in water going to be broken down into? H2 plus O2. These are both diatomic elements, so you've got to write the 2's behind them. How would you balance this? Put a 2 in front of water because of the 2 oxygens on the product side. This now changes hydrogen. Put a 2 on this side to make 4 hydrogens on each side. Again, this is decomposition because you start with the compound and it breaks down. If you think of something decomposing, it's breaking down. Mercury 2 oxide, what will it break down into? Well, first let's get the formula. Mercury is +2, oxygen is -2, metal with a nonmetal, so this is an ionic compound. When I cross my charges, it's HGO. It breaks down into Hg plus diatomic O2. Again, I'm thinking about single atom, diatomic element. to balance, I have to put a 2 in front of the HGO because of this 2 over here. And what else needs to be done? A 2 in front of the Hg. The next type is called single replacement. By definition, one type of atom in a compound gets replaced by a single atom. So, for example, sodium chloride is a compound and lithium is a single atom. What happens is lithium is going to replace sodium. Sodium will be taken away from the chlorine and lithium will take its place. So, whereas I start off with Na with Cl plus Li by itself, now Na is by itself and lithium is with the chlorine. I knew it was LiCl because lithium is positive 1 and chlorine is negative 1. Here is another single replacement reaction between the solid lithium and the aqueous solution zinc sulfate. What do you think is going to replace what here? The lithium will replace zinc because they're both metals. So lithium will take zinc's place. Zinc is now going to be by itself. I just write the symbol as Zn because it is a single atom. And we have a new ionic compound, lithium sulfate. Cross your charges. La2SO4 because sulfate has a negative 2 charge. This is a pretty easy balance. You just have to put a 2 in front of the lithium. So again, this is single replacement because lithium replaced zinc in the ionic compound and now zinc is on its own. What if zinc tried to replace lithium? It doesn't go both ways. Remember when we talked about the electronegativity and the first ionization energy, those periodic trends? Remember that lithium is an alkali metal, so lithium's very, very reactive. It wants to bond to sulfate more than the zinc does. So even though zinc sulfate can be a compound, zinc is not favored over lithium to bond with sulfate. So if zinc tries to replace lithium, it will not be able to do it. Now moving on to double replacement. The cations from two ionic compounds trade places. Remember in single replacement, you started with a single atom with a compound. Now you're going to be starting with two compounds. So sodium hydroxide plus potassium carbonate. The sodium and the potassium are your cations. They belong to the two anions now, hydroxide and carbonate. But when they're combined, they actually switch partners. So now sodium is with carbonate and potassium is with hydroxide. Paying attention to our charges, we write it out as Na2CO3 plus KOH. And now think about balancing. A 2 in front of the NaOH and a 2 in front of the KOH. Pause and try it out for yourself. What do you think will switch in this one? Remember, in an acid, hydrogen acts like a cation. That's sulfuric acid. Sodium and hydrogen are going to switch places. Sodium sulfate and hydrogen with hydroxide is HOH, or we could just say H2O for water. In this case, I'm going to leave it as HOH, and the reason I do that is because I have a hydrogen ion and a hydroxide ion on my reactant side. It's going to make it easier for me to balance the product side. I put a 2 in front of the Na, I put a 2 in front of the HOH, and I have a fully balanced equation. Lastly, we have combustion reactions. By definition, oxygen reacts with another substance. often producing energy in the form of heat or light. Specifically, we're going to look at the combustion of the hydrocarbons, compounds made up of carbon, hydrogen, and sometimes oxygen. The reactants are always the hydrocarbon and oxygen, and the products are carbon dioxide and water. So here's an example. Automatically, I know my products are carbon dioxide and water. Combustions, we always balance the CHO and leave oxygen for last. This side has 6, 6, and 2. And remember, the product in a combustion is always 1, 2, 3. So we've looked at balancing combustions before. Starting with my carbon, I put a 6 in front of the CO2. That makes my carbon count 6 down here. It will change oxygen, but since oxygen's going to change again anyway, I'm just going to exit out, come back. If I put a 3 in front of the H2O, it gives me 6 hydrogens. And again, I've changed my oxygen. Now let's get to counting that oxygen. We have 6 times 2 here, that's 12. Here we have 3 times 1, that's 3. The 12 from the 6CO2 plus the 3 from the H2O give us a total of 15 oxygens. Uh-oh. We have that odd-even problem. Remember, if this number is odd and we can only get an even number of oxygens, then we have to do that process called bump it up. So what we have to do is go way back to the beginning of the equation, and I'm going to put a 2 at the very beginning. Now I have 12 carbons and 12 hydrogens instead of 6 and 6. To fix it on this side, I put a 12 in front of the CO2, mark it down here. Oxygen will change, so I just exit out. I put a 6 in front of the H2O. Now I have 12. Again, I'm going to have to recount that oxygen. Well, in this case, I have 12 times 2 is 24. 6 times 1 is 6. 24 plus 6 is going to make my oxygen count into a 30. Now to fix the other side, I have to multiply 15 times 2, and now I have a fully balanced combustion reaction.